I just have a brief things on certain important things on a machine learning. Those who have studied a machine learning, probably they know there are two important things which you can do in machine learning. What are the two things? Classification is A, then regression. Okay. So, what are the different type of classifications?
Binary classification,
Okay. How you do a classification?
in any separable point A and point B. Two types of class A and class B we separate.
Okay. See, there are different types of classification. One type of a classification major is there's a clustering on that. Okay. There are clustering by, that means future extractions and classification can be done by a clustering. There are different type of clustering. The one standard clustering which everyone studied is a k-means clustering. Am I correct? Those who have studied machine learning, fundamentals of machine learning, there is a standard clustering technique, a k-means clustering. Other than that, there are other clustering techniques are there, which I am going to explain it one on that, clustering with a partition on. Okay. There are other techniques like spectral based clustering techniques are there. Newman clustering technique. Anybody heard about the Newman clustering? Gorman-Newman, it is a very famous one. Okay, it is a very improved Gorman-Newman clustering techniques are available. Okay, this is all used the very recent machine learning algorithms on. Okay, so my idea is, what is a clustering? What is a click? From the idea of a click, we will go for a clustering. I will just mention an algorithm for clustering. Okay, the measure of the clustering. Yesterday, Bindu was showing the how to calculate the clustering coefficient. Am I correct? She was explaining on with your data, Facebook data set, you can find a clustering coefficient on that. Okay. So, you have done a hands-on session yesterday, the theory part I will just explain it. Then there is a major part of clustering called data partitioning. Okay. Data partitioning is this. So, I will explain one a nice algorithm, it is a real time algorithm for data partitioning via graph partitioning on. Okay. This is the idea behind it on. Okay. So, what is a cluster? Generally, we say that we have COVID clusters are there, we have identify the hot spots of the COVID clusters on that. Okay. So, what do you mean by that cluster? What a group of related one. Any other? For example, you have a large data on that, I want to cluster the data. Why you want to cluster the data? What is the purpose of clustering the data? It is a general question. To group the similar data. Why you want to have to study the similarity on that? So that you can place it in particular category. Differentiate. See, when you want to study how a group of people is reacted on that. Okay, let us look into the as a social network on that. Let us take it's a famous network, like you may heard about the city club network. You have a city clubs like a Lions club. Every city there is something called a city clubs on that. There thousands of people will be there in the club on that. You can look as a network. Okay, each member of the club is a node, and then two members known, even though they are a city club, they may not know each other. For example, if you look into the Lions club, okay, if you look Lions club of Coimbatore, there may be some 10,000 people will be there, but all the 10,000 may not know each other. Okay, so if the persons are the node, if one person is friend of that, okay, then there is no edge between that. That means a link between on that. Okay, now you can apply this clustering algorithm. You see that among the Lions club, who are all the friends of that, and how many friends? Why it is needed is, suppose you want to have a president's election for the Lions club. Okay, somebody want to contest, then you know that who are all the influential groups on that. Okay, this cluster you have, see this out of 10,000 you have, there are 1,000 people known each other on that. Probably you may able to target on that. There are some 500 people are known each other on. So you have a clusters among the bigger network. Probably you can target them and then campaign them for something else on that. For example, you want to do a presidential or secretary election for a club. you try to identify instead of writing to all, maybe you have you try to identify the cluster and then you just contact the cluster people, you may be able to get it on. Okay, that's the basic idea. This is an example. This can be extended to the any other data network on that. Okay, on either it's a medical based on or a financial based market on. So that's an magic. So I'll just give what is before going to the cluster. There's something called a click, and then from the click we'll go to the max click. Then we'll go to the cluster. Then I'll give an partition on this. This is an idea. Okay. This is an example of you have different clusters on that. Okay. So, anybody knows what is a click in a graph? I come to the graph theory part. What is this click? No, you heard about it or not? Okay. It is basically a click is a complete subgraph in the graph G, complete subgraph of that. So, you have a K2, a complete graph of 2 vertices, K3 complete graph of 3 vertices, something on that. So, it is a complete subgraph. Now, I am interested on the maximal complete subgraph on that. So, how many complete, there are so many complete subgraphs will be there. What is the maximal on that? Okay. I think already Professor Venkatesh Ramana has mentioned about the difference between a maximal and maximum. Am I correct? So, I am not interested on the maximum, I am just finding a maximum on it. Okay. So, based on the optimization and uniqueness, you can do that. Then the cardinality of this becomes we call as a click number. Basically, this is a NP complete problem, that is hard to find on that. I think he also mentioned what is a NP complete on. But there are cases where you can reduce into a polynomial time, okay, on n log time on that I will show an example of this particular case on that, just an exposure of that. Okay. Let us look into a small example. Can you guess what is the max click, what is the size of the max click or a click number? For example, I can label this is A, B, C, D, E, this AB is a click, am I correct? Is it a click? Yes. And then this ABE is a click, am I correct? This K3 is inside on that. Is it K4 is inside? You may can look into that. A, B, E, D. See, you will see that there is a K4 inside it. Okay, so this is therefore this click number is 4. It's a very fun. You can probably see that there is a max click is this is a click of K2. You have a K3 is there, and then you can K4. So, this finding this click is very interesting probably. If you look into this graph, so you see that there is a click of size 3, click of size 3, of course, click of size 4 also this. You have a different size of click 3, then it's size 5 is there, K5, I do not think K5. See about K5 inside? No, I think. If you look into this graph, okay, you have, you see that there is a K4 inside it on that. Okay, so the click number is 4 in this case, the previous also click number on. So, finding this is a very interesting one. So, as I told, this finding this click is basically a hardest problem in computer science. NP complete on that, but there are some cases. I just show an example. Then we'll go to the clustering on. Okay, just interesting on. This is we just take an example where you can find a click number in a polynomial time. Okay, that's we called as a interval graph. Interval graph is a graph derived from an intervals on. Okay, just you take the vertices as intervals. okay, and then two intervals are intersect, then there is an H between the two intervals on that. See, for example, you just look into this I1, maybe I take this is I1, then I2, maybe I3, I4 and I5. If you take a number line, just listen, and this is 0, 1, 2, 3, 4, 5, 6, okay. The interval is maybe I will just, this is an I1, I2 is 1 to 5. Is this I1 and I2? Sorry, this I1, this is I2. Are they intersect? Of course, the intervals are closed one. I1 and I2 are intersect or no? Yes or no? Is there any common point? At least one is there. So, it is a closed interval. So, one is there. So, there is an H between 1 and. So, I1, I3. I1 is here and then see the I3. I1 is this is an I1. Sorry. I3 is 0, 2. Are they intersect? Yes. So, there is an H from I1, I3. Then I1, I4. Yes, I1, I5. I1, I5. I1 to I5. See, I1 is 0, 0, 1. I5 is 2, 3. Are they intersect? So, you do not have any H between I1 and I5. That is like that you form a, for a given graph, you can label as this intervals are the labels. It is a very beautiful graph. It has a lot of applications in data science because most of the data are in an interval form on that. You may not have a real time data. You may not have it. For example, I want to measure the temperature in Coimbatore or in Etimadai. Sometimes we may able to measure it exactly. Sometimes we may say that it is between this and this, probably between 30 and 35 today, maybe 25 and that. What is the rainfall on that? Between 10 and 12 is expected on. So, you can have it on that. Once you have, you cannot have a real time data, real time this exact value, probably you can have data with an interval on the specific. So, this interval data approximations and things like that are very famous on that. So, based on the intervals, so there is an interval on regressions and things like that, the interval approximations are there. So, this data on intervals are very different one. Okay. So, you can interpret this as a graph on that. Okay. So, I just, so this is a graph corresponding to this. Okay. This is another example of an interval graph. So, the intervals are given. See this intervals A is given, B is given, C is given. Probably you know that see A is in A, B, C are intersect. So, there is an H from A to B, A to C, and then A is intersect with D. So, there is an H between A and C and things like that. Okay. As I told, this has a lot of application in electronics and predictions and things like that, even a data science also has applications. So, now I am interested on finding the max click or a click number. Can you guess what is a click number in this graph? Click number. It's a graph with 7 vertices. Am I correct? Can I have a K7 inside? Complete graph on 7 vertices? Yes? No. Okay. K5 is inside? K6, K5. Can you find K5 inside? K4, complete graph on 4 vertices. Yes or no? No. So, only K3 is there. So, this click number of this graph is 3. This you can probably you can just look into that. What you can do is you just take this lines and see that what is the maximum number of intersection. The maximum number of intersection gives a click number on. That is the logic on that. Okay. So, based on this logic, there is a small algorithm which I will show you. That's called the left alignment algorithm, which takes a polynomial time. It's a very famous one for an interval graph on that. Okay. So basically, you take the intervals and then make it in a real line, and then try to find which intervals are there. Okay. Then you know that, for example, this intervals, the vertices corresponding to this intervals form a clique, the vertices corresponding to this intervals form a clique, like that you have an, okay. If there is an intersection with the 4 intervals, it means that the clique of size 4 is inside it. That is the logic. Is it clear? So, this is a very famous one. In fact, it has used lot in electronic design and things like that recently on. Okay. So, this idea of this, I will just given a brief idea of how to find it clique. This is a basic idea. Just take the interval and try to sort it on the based on the left and right. Okay. And then then you change the clique and max clique. If you start with the clique is 0 and max clique is 0, and then if your value, the first sorting values is left, then you increase the clique by 1, otherwise you just keep as it is. Your clique size is more than the max clique, then you change this max clique as a clique, otherwise you just keep it on. Okay. This is a very interesting one. For as I told, finding a clique number in a general graph is difficult. Of course, there is no algorithm, only an probabilistic methods are there, but still for an interval graph it is possible. This is a, so just a small example I will show you. If you look into this graph, okay, if you look into this graph, this interval, see this intervals I am just sorting according to this intervals. Okay, so it is a left hand side and right hand side. For example, if you look into this 0 is here, which is left on that, and then there is another 0 which is on left, and then you have 3 ones are there. There is 1 1 on the right hand side. So, I am just giving a priority on left right, and then another 1 on, there are 2 ones on the left hand side. We have 2 ones on the left hand side. So, like that, then we have a 2, 1 2 is on left hand side, 1 2 on the right hand side. So, I am trying to write it on that. The logic is this, the same as I told. The logic is you finding this intersection on that. You just find the intersection on that. You know how many lefts are there, how many rights are there, is there any intersections. Okay. So, you can find the number of intersections. Basically, that's the logic behind it on that. So, just apply this algorithm, probably you know. So, just make it see, first one is a left hand side, I increase the clique by 1, then max clique is there. So, I just go on doing that, increase the max clique because of the 4 left hand side. Now, my sorting gives a right hand side. So, I just keep max clique as it is, clique I reduce it. So, this is a famous algorithm on it. Okay. Anyway, I will share the slides and then PPT. Okay. Now, this based on the clique, probably you may able to find a clustering coefficient on that. Okay. Clustering coefficients can be viewed as a part of a clique. Okay. How to find a clustering coefficient, which we already discussed yesterday. Bindu has shown an example on that. So, clustering coefficient is one measure which I told in a network. Clustering coefficient is how these people, the communities are close to each other, which community is the larger community on that. Okay. Give an example as I told, if you look into this, for example, if you look into the Lions Club of the southern India, okay. So, which Lions Club is more powerful in terms of interactions, in terms of number of people and things like. So, you can have they form a community on that Lions Club of Chennai or Hyderabad, maybe they have more people and then they are more powerful on that. So, probably you can do something with them, that is the logic on. So, the clustering coefficient is one of the important parameter for future extractions and future selections in your data science on. Okay, this is a lot used in this machine learning techniques. Probably when you come to the higher semesters, you learn it this. Okay, this is the. Okay, there are 2 type of a clustering which I have mentioned in this one. Okay, one is a local clustering, other one is a global clustering. Local clustering you can do by number of links between the neighbors. Okay, The global clustering is just find all the local clusterings and then divide by the total number on. That is the logic on that. Okay, so let us look into this. Maybe I have a graph. I think I have a graph example. Okay, I just go an example. If you look into this graph, I take it something like that. I just label A, B, C, D, E. Anybody can say what is CA? Denominator is 5 choose 2. Denominator is 5 choose 2. What is the numerator? Number of links between the neighbor. How many neighbors for A? What are the neighbors? So, including A, when I say a neighbor of A is a close neighbor on that. So, there are A, B, E. Among this A, how many neighbors on that? You have A, B is there, A is there, and then B is there. So, what is it? So, how many links between this three? Okay, so 3, this one. So, if you look into this, for example, I want to find CB. Again, this is 5 choose 2. How many neighbors for B? How many neighbors for B? There are all the vertices are neighbors of. Okay. Now, among this, okay, so how many edges on that? How many edges between the neighbors of B? Of course, is 7. Okay, this is a way we can calculate it on. Okay, this is called a local clustering on that. Once you find the local clustering of that, okay, this has to be, of course, this has to be. I have to change it into small n. Okay, then you find CC, CD, and CE. Then you just this global clustering is you have CA plus etc. plus CE divided by this 5. It's something like an average on that. Okay, this is a very powerful measure for finding some features in a data on that. Okay, the data comes from, as I told, this is as a protein network or a transport network or airline network or a game network. This measure, finding this clustering coefficient, is a very important one. Okay, is it clear? Let us just take one or two simple example. Let us take Kn is a complete graph on that. Okay, probably I draw K5. Sorry. Maybe somebody will help me on what is the clustering coefficient of A, B, C, D. Clustering coefficient of A. Immediately you can guess it. How many neighbors for A? Including 5. How many edges between the neighbors? C of A. It is 5 choose 2, of course, correct. Denominator, numerator, it's also there are. Am I correct? So, clustering coefficient of all are 1. Therefore, the global clustering also 1. That means there is a 1. If it is 1, you mean that all the members are interact to each other. Everyone knows each other on that. That's the best model. Okay. When you want to extract certain clusters, listen. When the clustering coefficient is high in the sense if it is 1, then I say that all the members are known each other on that. That's the meaning. If you look into the community, okay, there are 100 people are there. That 100 people form a cluster. And then the clustering coefficient is 1 for that community. It means that everyone knows each other. So, it's easy to just approach a one person and then send the information to one person. Probably he may able to transmit to all other ones. That's the beauty on this clustering coefficient. Very powerful coefficient on. Is it clear? Okay, let us look into this one more example. This is a famous graph. Okay, so I am not taking a graph theory course, but I just give an example on that. This is a Cn. So, what is the clustering coefficient of 1? Ca, C1. Sorry. How many neighbors for the 1? There are 2 neighbors. Am I correct? How many edges between these 3? 1, 2 and n, 2. So, it is 2 by what is the denominator? N choose 2 on. Okay. So, it is the same on that n choose 2, n choose 2, n choose 2. So, it is all are same. So, which has more one this here is this n choose 2, in this case it is 1, which is a powerful one. Which suppose I have a community which is a cycle community, I have a community of a click community on that. That is what I was explaining the click on that. This is a click, this is a cycle on that. Which community is powerful on? Click community, because it has a this clustering coefficient is more on that. Okay. So, this is a one interesting thing. Similarly, you can try for the other graphs. This is I prepared for my class. So, I try to repeat that. Okay. Now, so based on that, probably as I tell, you can talk about the community deductions on that. Community deduction is which among the large one, which one have better community, which have community on that. Okay. This is a very influential factor in that. I am not going to the very detailed one on it, particularly for a large network. Okay. For example, if you look into this graph, it's a network on that. They form a one community on that. This form is one other community, this form is on that. Okay, which they have a different clustering. What is the clustering coefficient of this community? Clustering coefficient of this community. Can you guess? I take this is maybe community 1 or community A, B, C. This is you can have 1, 2, 3, 4, 5. What is C1? C1. You just look into the smaller subgraph on that. You do not require the such. You just look into the C1 is denominator is 5 choose 2. Am I correct? What is the numerator on? What is the numerator on? 5. Like that you find it on that, then you find C1, C2, then you can find a global community on the capital C of 1, here capital C of CA, sorry, CA and CB, and then you can see C, you can find out on that. Okay. This is from that you can measure that which community is powerful, which community is influential, all type of analytics you can do it on that. It's a very interesting community detection on. Okay. This has applied on, as I told, in the internet citation network, transport network and things like that on. Okay. So, these are all the few examples for a community you can. Okay. Probably many of them have heard about this Karate Club network. Okay, if you work on this data and data network, probably you know there is a beautiful on dolphins network. Okay, based on the dolphins movement, you can find on that. These data are available, and then there is a web page link on that. Web pages form the nodes. If the one web page is giving another link to the other one, for example, this ACM we have a 2 website on this school have a 2 website. One is hosted by Amrita, one is hosted by ACM. Okay. ACM you see if you click there you will get the link of this. If you click here there is a link on that. So, there is a link on that. So, if you click and goes to the another web page, then there is an H between that, that is called web link on that. So, it's like that. Okay. You will see that this community, see if you look into this one, probably you will see that a larger community is here on this, a larger community on this. So, then you know that which are the websites are is likely to give a internal link on that. One link is to another one, another link is to another one and things like that. If you want to see if you look at this web page, now from this web page you want to access, you have to go to one by one. You have to access this, you have to access this, then you have to access and then you have to reach it on. That's the different ways on that. Okay, this is a way. Similarly, network associations, there are different ways on that. So, finding this best community structure is one of the interesting problem in data science, okay, particularly on a large scale network. As yesterday I was explaining what is a large scale network. When I say a network, a data network is a large scale. Yesterday I was explaining based on the degree. If degree distribution of that network follows power law distribution, if a degree distribution follows a power law distribution, then I say that that network follows a large scale. Okay. So, most of the social networks, and then this real world networks are basically a large scale network on that. Okay. So, I think I have explained it. So, finding this community is one of the interesting one, probably you can explore it when you want to do it on that. Okay. So, there are a lot of different approaches are there which you will study in machine learning. One is graph based method which I am going to do. This is what I am planning to do, maybe another 15-20 minutes. Then there is a spectral based method. What is a spectral based? This is for any structure you can visualize as a matrix, which we have been looking on that. Particularly Deepak also shows that for a given data you can just look into that, then you can use some linear algebra techniques, okay, particularly using the eigenvalues and eigenvector you may able to do that. Okay. But I am interested on this first technique on that, finding the community detection by partitioning. There are hierarchical clustering. This is a very famous clustering in your machine learning. So let us learn the machine learning, probably they know what is hierarchical clustering. Yes? Anybody heard about that? Hierarchical clustering?
Clustering, we do some clustering level mapping.
Clustering, okay. Then there is as I told, Garvan, Newman, it is a very famous clustering technique. This is a one very recent one, which has a less computational aspect than other things. Then Newman fast algorithm is also, there are different clustering algorithms are there on that. Okay. So, in that probably I will just explain what is this. So, using KL algorithm for a partition, how you can find the different clustering on that. Okay, that's the motivation. Is it clear? Any doubt? So, you start with the click. From the click you move to a cluster. You find what is a clustering coefficient for a local clustering coefficient and then global clustering coefficient. Why it is important? Because you want to find the community detection. Ultimately, community detection is the primary motto for a large scale network. I am talking about the large scale network because data science is, as I told Professor Venkatesh and other people, your data may not be at 10,000 or 100,000, probably in billion. Then you need to imagine that. Of course, imagining this, visualizing is difficult. As I told, even you have a sophisticated tool, you may not, but you may able to extract certain values on that, which node has a high degree centrality, which node has a more clustering, which are the nodes form a community and community structures and things like that. Okay. From that community detections, probably you may able to extract certain futures or you can do some predictions on that. So, one way of doing the clustering is this partition on that. Okay. So, this there are general partition. I am not going for a general partition. I will just take a two-way partition. From that two-way partition, you do it recursively. We can do a general partition on that. Okay, that is the logic. Okay. So, this logic is, suppose you have a data. You have a data points on that. Now, I want to partition into I just want to partition into four different sets on that. So, what I do is this KL, using KL I try to make it into 2. Okay. You have set A and Y, that is called two-way partition. Then I try to apply the same thing, then I make it into something like x1, 1, this is you take x1 and then y1, this is y1, 1, something like that. Then you can recursively do that, you can see that you will get a required partition on that. Of course, there are some fundamental assumptions are there, probably if you are interested you can just look into that. Okay. So, we are interested on K-way partition. K-way partition is for a given network or a given graph. Okay. You try to partition this nodes into K equal parts, okay, or a different size on. Okay. So, basically finding this K-way partition is a NP complete problem. Okay, even as I told, click itself is NP. So, this is but still I am interested on a polynomial time algorithm. This is general on those who are working on computer science. General problems are NP complete, but certain cases you can reduce into a polynomial time. I will just give another example for a polynomial time algorithm. Okay. This is we take it as a two-way partition. So, the logic of this partition is this is the partition. You try to partition the graph such that the interconnection edges, okay, the weights is to be minimized on this. So, I want to minimize this. Okay. I will just give an example, do not worry. and this minimization value we called as a cut cost on that. So, basically you have to reduce the cut cost on. Okay. So, if you look into this graph, okay, so I want to have some partition, probably I will do this way, one partition, then I can make it another partition, then I can make it another partition. This is generally a multi-way partition on that. So, this is the logic behind it on that. How you can make it a graph? When I say a graph, please imagine this is a data network on that. You have a data, from the data you can extract it. Yesterday, I think from a Facebook data, we learned how to extract the graph on that. From the once you have a graph, then probably you may be able to do all those things. So, this is a three-way partition on. Okay. So, I am interested on bipartition or two-way partition on that. That means you have a graph where you take the set of edges, remove it, so that the graph becomes a two-way partition such that the total cut cost is minimum. That is the like. It is a very famous Kernighan link algorithm on that. So, I am not going to the detail of the algorithm, probably if you can look into that if you are interested to work on that. The algorithms is basically, it is suppose you have a graph, the algorithm works on that. You take a initial partition, okay, maybe I just switch it on. Okay, this is your initial partition, something like A and B. This the logic is done that. Now you try to find the nodes here and nodes here with the internal cost. That is something called the internal cost. Internal cost is the cost associated with the internal nodes on that, internal within this A, and then EA is the cost associated with the external code. That means, suppose I have a node X here and node Y, node X in A and node Y in B, then what is the cost corresponding to that? The cost, for example, suppose you have like this, you have something Z and then this is T, this is 2, 4, 1. Then EX, that means external cost of this X is 7, like that. So, you try to find the internal cost and external cost, then you find the difference. This dA is a difference on that, okay, difference of the internal cost and external cost. Then you find the gain on that. What is the gain? This is the most important one, that gives how the difference is there, because you want to improve, you want to optimize this difference. Suppose you have a network, you may have something A and B. Now you try to optimize this partition, optimize this, that means you want to find the minimum cost on that. So, for that you have to use this gain function is the most important one, because we repeatedly use it, that is the different cost for that node, and then you find it. So, based on that this algorithm works on that, you just find this gain value, then improve the gain value by swapping two vertices from the set A to the set B, you just swap it, okay, and then you will try to swap the vertices and then repeat it. So, it's recursively you can do that. Okay. I am not going to the detail of this algorithm, just this is if you record it and then you try to find the partial sum. Okay. This S is this is sum of this gain, the sum of the gain value. If the sum of the gain value, you find the sum of the gain value. If the sum of the gain value is positive at every point, every node, okay, then you try to swap it with the node which corresponding to the maximum on that. So, this is a swapping process on that. Okay. When you process and see that if this is this capital S is less than 0, then you stop it. That means further swapping is not possible. That is the logic on that. So, you have an initial partition, now you try to swap it, some vertices from this side, some vertices from this side, you go on swapping such that the total cut cost is minimum on that. It's a very beautiful one on that. It's a very useful for a data partitioning. It's a real time on this. A lot of people are using on that. The advantage of this is that complexity is there. This is the order of n cube is there. N cube is comparatively less if you take a larger data. Of course, you can make it as a proper this, as I told like yesterday, you can use some specific sorting methods like quick sort or some sorting method you can reduce into n square log and on. Okay. So, this is based on certain data structure, you can use it on, okay. Maybe heap sort, if you use a heap sort, this you may get it this. Okay. Yesterday also I was explaining the heap sort method to reduce it on that, okay. Particularly if you use this Dijkstra's algorithm, generally it is order of n square. If you use a heap sort, probably you can reduce into order of n log n, okay. That's the logic. So, this is a flow chart of the algorithm, okay. There's a later part of that, by improving better data structure, it is improved to order of n square. Let us look into a small example, probably I'll wind up on that. This is my graph, okay. So, my set A consists of A, B, C, E, A, B, C, and B consists of that. Probably we will calculate the internal node, okay. So, what is I of A? Anybody? What is the internal cost of this node A? How many vertices within this group A? For A, you have A is there, B and C. So, what is the internal cost? See A, B and A, is there any H between A and C? So, only you have A, B. So, what is the internal cost on that? So, only one edge is no, so you have internal cost is 1 because 8, and then external cost of A. From A to the other group. For example, if you look into that AD and AF, AD is 1 and AF is its 5. So, now I find the D of A. What is D of A? I just move it into an example. What is D? EA minus IA. External cost minus internal cost. Yeah, it's 4. So, like that you calculate this D value to every node in a graph on, okay. That is what I am interested on. Probably I will just show you an example. If you look into this one, you have an internal cost and external cost. So, internal cost of every node is here, external cost is there, then there is a difference on that. Okay. Once you know, then you can find the gain value. Gain value you can calculate as a pair on. Okay. So, gain value between gain for a pair of that means AD from A is on one partition and then D is another partition. So, between the two partition, how many nodes are there? I am finding the gain value. Then I find the total gain based on that. If the total gain is positive for all, you try to improve it, otherwise you stop the algorithm. That is the procedure on. So, I do that in this way. My first gain value itself, my first sum itself is positive. Okay. Now, if you see, for example, what is S1 is 2, what is S2? S2 is 2 plus minus 3, it is 2 plus minus 3, it is negative. S3 is negative and so on. If you take S9, everything is negative except S1. That means you try to, this is a try to swap these two vertices on that. So, I am trying to swap A on the other side and D on this side. Okay, this is a swapping process. So, from this pleasant this partition, I am trying to swap it. I am getting this partition. Just you have a swapping on that. Okay. Now, repeat this procedure till this S is negative. Then you stop algorithm. That gives a beautiful partition. It's called a two-way partition. It's a very famous algorithm. It's used a lot of places in a data clustering, data partitioning, and things like that. Particularly on advanced machine learning courses on that. Okay, this algorithm replaces your traditional hierarchy, k-mean square algorithms and things like that. Okay, this in terms of computational complexity, of course, this order of n square, but still can be compromised. So, when you do it recursively, probably you may be able to do that. See here all the gain values are negative. So, the sum always negative yes also negative, then you can stop the algorithm. This is a procedure. So, this is the best way partition. The minimum cost is 1, 2, 1 and 5, therefore, it is 9. The cut cost is 9 odd. Okay, this is the way easy. I am just giving an example. This is a two-way partition, but this can be enhanced into a multi-way partition. That's okay. As a multi-way partition for a hypergraph, what you can do is for a given graph, you take it in a different ways. Okay, do it recursively. You can do that's one way. Or Cariffs has given George Cariffs is given a nice algorithm. So he given this, that's called coercing method. I'll just explain it in graph. So you have a partition. You try to partition and then make it into a smaller one. It is like you have a hashing technique on that. What is a hashing algorithm? You have a bigger node or bigger data, probably you map into a smaller one. Am I correct? Then you take it in a reverse way. The same logic. You have a graph. You try to apply the scale algorithm and then try to take it into the sequentially make it into a smaller one. This is a coalescing phase. Then you can do it and uncoalescing on that. You try to extract it. So this is similar to the logic. It's not hashing, but similar logic is there on. Okay, using this you may be able to do a better partition for a multi-way on that. Okay, this is one. These tools are available when if you visit to George Cariff's lab on that. Okay, this is a one interesting and important algorithm for a machine learning. Of course, recent Garvan-Newman algorithms and improved Newman algorithms are there, but certain cases they use this KL algorithm for a data partitioning or data clustering for a community detection. Okay, this is a coalescing basis and H coalescing basis, and then probably this is an example you can reduce into a smaller one and then you can make it into bigger one on. Okay, so apply this initial partition in a different way and then you will do it on that. Okay. Okay. Yeah. Any doubt? Any clarification? These codes are available. If you are interested to work, probably I can give a code. This code on C and Python are available. It's easy. Multi-way you can do it on that for a data clustering and data network on that. This you have implemented for certain data and data network with my master students and things like that. Any doubt? Okay, thank you.